Lesson 6.2, Apply Properties of Rational Exponents. We're going to use the properties we talked about in Chapter 5 in this chapter as well. So let's do some review from Lesson 5.1. We're just going to go over a couple of the properties that are pretty common in this chapter. The first property that we talked about was multiplying like bases. To condense that product down to one term, you would add the exponents of the bases together. When you divide like bases, we do the opposite. We subtract. Remember, it's always the numerator exponent minus the value of the exponent in the denominator. When you end up with an exponent that's negative, to make it positive, we take the reciprocal of the base. So be careful on this one. Since your exponents are going to be fractions, if you end up with a negative fraction exponent, you're taking the reciprocal of the base, not the exponent. Rational exponents mean, like I just said, we're working with fractions. So think about common denominators when you add and subtract. If you feel like it would be beneficial to have all the properties from Chapter 5 with you, I would pause the video and grab your note packet. Have Lesson 5.1 ready to use as we go through these 6 examples. We're asked to simplify each rational expression using properties of exponents. In our first example, we have 7 to the 1/4 times 7 to the 1/2. Since the bases are the same and we're multiplying them together, we condense it down to the same base of 7 by adding the exponents. So this would equal 7 to the 1/4 plus 1/2 power. And again, just like 6.1, I know it's going to be challenging to write those exponents like smaller than the normal number with the fractions. Please just try your best. To get a common denominator, we need to figure out what both 4 and 2 go into. We could convert 1/2 to a denominator of 4 simply by multiplying the top and bottom by 2 over 2. And that would give us 7 to the 1/4 plus 2/4. Wow, in my head I was thinking the answer already. 1/4 plus 2/4. Sorry about that. When you have a common denominator, just add the numerators together. This simplifies then to 7 raised to the 3/4 power. And that's as far as you go. Now in the next example, there are a couple things you could do here. You could add the insides and then do the power on the outside, or you could distribute the power on the outside into both of them and then get a common denominator. It's up to you. I always like to condense the inside down to one base if possible, and we can do that by adding the exponents together. But keep in mind this stays in the parenthesis until we're done. That means it's 6, there we go, to the 1/2 plus 1/3 power, and then all squared. A common denominator of 2 and 3 would actually be 6. That means we have to multiply 1/2 by 3 over 3 and 1/3 by 2 over 2. There we go. I knew I'd get there eventually. Keeping our base of 6, if we take 1 times 3, we'd get 3 over 6 plus 1 times 2 would be 2 over 6, and then squared. 6, goodness gracious, people. What am I doing here? There we go. Now we're in business. Now if we add the numerators together, 3 plus 2 would be 5 over 6. That gives us 6 to the 5/6 power, and then we square that answer. What that means, if you have a power on the inside and a power on the outside, we multiply. A couple of things with multiplying. We actually don't need a common denominator this time. But if you have a fraction times a whole number, so 5/6 times 2, put the 2 just over 1 and then multiply straight across. That would give us 6 to the 10 over 6 power, and that fraction reduces to 6 to the 5/3 power. Make sure we can see that. I just want to make sure that 5 is a little bit clearer for everybody. There we go. We'll try this one. There, 6 to the 5/3 power. Applying more than one property of exponents. Remember on the last example, I said we could either simplify the inside or distribute the 2 in? Be careful on this next one, 4 to the 5th and 3 to the 5th. Notice our bases are different. So while you could take 4 to the 5th power times 3 to the 5th power, you'd get a pretty big number. I would recommend in this scenario actually distributing the -1/5 in, and you'll see why in just a moment. If we have 4 to the 5th power, I'm going to put 5 over 1, times -1/5, that's going to equal 4 to the -1 power. The 5s would cancel out. Times 3 to the 5th, I'll put 5 over 1 to the -1/5 power. That's 3 to the -1. Now we just have one exponent for each base, and they're both negative. So if we take the reciprocal of both bases, we would have 4 to the 1st times 3 to the 1st. Since those number bases are just 4 times 3, that would give us 1/12. We could simplify that all the way to that final product. Let's try the second row. 5 divided by 5 to the 1/3 power. Now we're dividing like bases. By definition, we subtract exponents. In the numerator, that plain base of 5 is technically 5 to the 1st power. If we subtract exponents, the rule is numerator minus denominator for exponents. A common denominator would just be 3. So if I multiply by 3 over 3, that would give us 5 to the 3/3 minus 1/3. And 3 minus 1 in the numerator is just 2. That ends up being 5 to the 2/3 power. We wouldn't evaluate any further because 5 to the 2/3 power would be a decimal approximation. So that's as accurate as it's going to get. Now this last one is definitely interesting. 42 to the 1/3 power times 6 to the 1/3 power, all squared. Taking a look at this, if we think about the exponent in both the numerator and denominator as being the exact same, we could actually use the product of a power backwards. So what we can do on this one is actually take out the exponent for the entire fraction. So watch what I do here. I'm going to take 42 over 6 and raise it to the 1/3 power. Technically, that's just the reverse of distributing the 1/3 power in. But then we have to remember that the entire value is technically being squared. What makes this a unique problem to solve is now the inside has no exponents to worry about. We can actually divide 42 by 6, and it's a whole number answer. We get 7 to the 1/3 power. And then that is technically being squared. If you have a power on the inside and a power on the outside, we multiply. So I'm going to put that 2 over 1 and just multiply them together. That would give us 7 to the 1 times 2 in the numerator over 3 times 1 in the denominator. 7 to the 2/3 power. No lesson would be complete without some crazy looking fraction to try to simplify. 6xy to the 3/4 divided by 3x to the 1/2, y to the 1/2. Simplify using properties of exponents. Right out of the gate, I see two coefficients. I see a 6 and a 3. They have nothing to do with the exponents as they are both raised to the 1st power. What that means is we're just going to take 6 divided by 3, and that would be 2 or 2 over 1. That gets rid of those two coefficients, and then we don't have to worry about them anymore. The x values, notice there's an x in the numerator, and it doesn't have an exponent with it. So we'll say that it's 1. To take the x's on top and bottom, we're going to subtract the exponents. That would be x to the 1 minus 1/2 power. And then we'll do the same thing with the y values. Y to the 3/4 minus 1/2 power. If we have the 2 out in front, 1 minus 1/2. If you guys can do that in your head, you don't need a common denominator. If you take half away from 1, we would have x to the 1/2 left over. Now the y values, if we take 3/4 minus 1/2, Make sure to get that common denominator. 2 and 4 both go into 4. I'll multiply that second fraction by 2 over 2. That gives us y to the 3/4 minus 2/4. And 3/4 minus 2/4 would just end up being 1/4. 2x to the 1/2 times y to the 1/4 power. So I guess it ended up not being all that bad. We end lesson 6.2 kind of like how we started lesson 6.1. Grab that power chart. You're going to want to use that to simplify the problems on this slide. It says simplify each radical expression using the power chart. Now remember we talked about finding values that are in the columns for each of the types of powers, either perfect squares, perfect cubes, fourth powers, and so on. It all depends on your index value. If the number if the number for that index is listed, go to that column and try to look at factors that are on that list. If you look at the perfect cube column, 135 unfortunately isn't on that list. And I know if I try to break this down, 2 doesn't go into 135, 3 won't go into 135, will it? Oh yeah, 3 does. How many times? 3 goes into there 45 times. Wow, 3 times 45. Hang on, I'll get there. There we go. All right, if we break that down into 3 times 45, neither of those are on our list. Try again. 4 doesn't go in. 5 goes in. 5 goes into 135 27 times. Notice 27 is a perfect cube value. If we rewrite this product then as the cubed root of 5 times 27, remember we can take out the perfect cube by taking the cubed root. The cubed root of 27 is 3. So 3 goes on the outside. That 5 is stuck on the inside. We're going to write that root symbol and put 5 on the inside. Remember that little 3 is the index, so that has to be there in that final answer. The simplified radical of cubed root 135 is equal to 3 times the cubed root of plain 5. In the second example, the fourth root of 27 times the fourth root of 3. Kind of like square roots, if they're the same on the inside, you can multiply them. If your index is the same, and notice it's a 4 for both of them, we can simplify this product by multiplying the insides together. It doesn't change the value of the index. 27 times 3 is 81. So this would be equivalent to the cubed root of 81. Cubed root, wow, fourth root, I don't know where that came from, sorry. The fourth root of 81. To try to evaluate the fourth root of 81, go ahead and look at your power chart, and that's actually on the list. What number to the fourth power is equal to 81? That answer would be 3. It's a perfect fourth root value. Gotta get perfect cube values out of my head. But then we go to the next one, and it's back to cubed roots. So there we are. The cubed root of 64y to the 6th. Sorry, everybody. We'll get there. If we have the cubed root of 64y to the 6th, what you want to do is split apart the number base and the variable base. Here's how we do that. If we take a look at the cubed root of 64 times the cubed root of y to the 6th, the cubed root of 64 is on our list. That's a perfect cube value. It's 4. And now with the cubed root of y to the 6th, think about your a to the m over n definition. That was from lesson 6.1. This means your base is y. The m value is the power on the inside, so the m is the 6. The n is the index, which is 3. We can reduce 6 over 3 to equal 2. Our final answer then is 4y squared. And that's as far as we'll get for the notes. We'll finish the rest of these notes tomorrow in class.